Hello everyone and welcome to the WUIVIEW video series. I am Giordano M. Scarponi, Assistant Professor in Chemical Engineering at the University of Bologna in Italy, and today my presentation is about hazards associated with non-natural fuels at the wildland-urban interface, with a focus on LPG tanks. At the wildland-urban interface, it is quite common to find domestic LPG tanks that are used as a source of heat and power for houses, especially in those areas like rural areas where the natural gas network does not reach. Analysis of wildfire or recent wildfire events, like those occurred in Spain, United States, and Greece, to make some example, has shown how, in case of contact with the wildfire front at the wildland-urban interface, this kind of infrastructure might be strongly affected.
When an LPG tank is exposed to fire, the thermal power generated by the flames is transferred to the tank structure and to the tank content. Within the tank, we have a liquid phase and a vapor phase. Both these two phases heat up and pressure inside the tank starts increasing. Commonly, LPG tanks are equipped with a pressure relief device, that is a valve that when the value of the pressure inside the tank reaches a specific value opens up in order to avoid and prevent tank pressurization. In this way, part of the content of the tank is released in form of a jet. Due to the presence of fire surrounding the tank, this jet gets ignited, giving place to a jet fire. While the valve is open, the pressure in the tank decreases, and this will be true up to a point where up to a value of pressure where the valve is supposed to close. During fire tests, it has often been observed a cycling process of the valve repeatedly opening and closing, opening and closing. However, if the fire is strong enough, pressure inside the tank might keep increasing despite the presence of the valve. At the same time, due to the fact that the fire heats up the tank wall a lot, and tank wall temperatures increasing up to very high values, the strength of the structure of the tank decreases. In fact, mechanical properties of steel, mechanical resistance of steel decreases with the increase of temperature. So at the same time, we have a decrease in the strength of the tank structure and an increase of the internal pressure. And we can get to a point where the curves of the strength and the pressure meet together, and at that point we will have tank failure.
After the tank fails, there are mainly three phenomena that can be observed. The first one, like you saw in the video in the previous slide, is a very strong explosion, also known as bleeding. And this is generated by the sudden expansion of liquid and vapor that are that come in contact with the atmospheric pressure after the tank fails. The second one is the fireball. A fireball is a specific type of fire, and it's called like that because of the spherical shape of the ignited cloud that you can see in the picture. The last event that usually occurs depends on the way the tank breaks, and is the projection of fragments of the tank far away from the tank itself. All these three events generate severe consequences, such as overpressure, thermal radiation, and possibility of impact onto structures and people in the proximity of the tank. It is therefore clear that we must put in place measures in order to prevent tank failure. One of the most commonly adopted measures in this sense is the definition of safety distances. That is a separation distance between the tank and any other object that could be ignited and generate the fire. As you can see from the table, different countries from all over Europe provides different values for safety distances according to the volume of the tank. What comes to the attention is the complete lack of harmonization from country to country. If we take as an example a 5 cubic meter LPG tank and we consider a safety distance of 3 meters, we can see from the table that this situation would be considered safe and in compliance with standards and, and prescription in Spain and Portugal. But this will be not true in United Kingdom, Greece, France, and Italy. That is, in some country, this situation is considered safe, while it is not considered such in other countries. And this, of course, is not acceptable. Another quite important issue here is the fact that maintenance is often left to the owner, but there is no actual control system in place to check that separation distances are respected during the lifetime of the LPG tanks. And it is not uncommon to find situations like those shown in the pictures where vegetation is left to grow uncontrolled in the surrounding of the tank.
So at the beginning of the WUIVIEW project, we formulated the following question. How can we assess if a tank is safe or not? In other words, how can we say, given a specific scenario and under specific fire conditions, if this tank will survive fire exposure or not? So in order to answer this question, we developed a methodology which is made of three different steps. The first step is the fire source characterization, in which we look at the fire and we calculate the heat load that this will have onto a tank that is exposed to this fire scenario. In the second step, the heat load calculated in the first one is used in a CFD simulation of the tank response. Data from the CFD simulation are then summarized into indicators that will be then compared with critical threshold values and will tell us if the scenario under analysis is safe or not. These two indicators are the weakened surface index and the pressure relief valve index. The first one is related with the mechanical weakening that occurs in the steel wall of the tank as this attains high temperatures due to the fire exposure. The second one is related with the fact that the second one will tell us how close we get to the point where the pressure relief valve opens. In fact, this event, the pressure relief valve opening, can be considered as unwanted in a wide and urban interface context. In fact, this will generate a jet fire that will increase the heat radiation towards structures and people like firefighters surrounding the tank, in the proximity of the tank. So we don't want to get to the point in which the pressure relief valve opens. But let us see with some example how the methodology works. For instance, here we consider the fire scenario in which a 1 cubic meter LPG tank is placed at 3 meters from a row of 6 Douglas fir trees. We also imagine that we have a wind profile that changes according to the distance from the ground, and we analyzed two different cases. In the first one, case A, the filling level of the LPG tank is 20%, and in the second one, the filling level is 80%. In this example, the fire source characterization step was carried out using the fire dynamic simulator developed by NIST. As you can see, the software simulates the ignition of the trees and the presence of the wind is also visible due to the tilt angle observable in the flame. Through the use of this software, it is possible to calculate the incident radiation that goes from the flame to the tank surface. This radiation is then used in the second step of the methodology to simulate using CFD the thermofluid dynamic response of the tank to fire exposure. Results from CFD simulations of the tank response provide very useful information. Among them, there are, for instance, pressure curves that shows us how fast and up to which value the pressure inside the tank increases. At the same time, we can have, for instance, like in the plot shown at the center of the slide, maximum wall temperature registered on the outer wall. In the case under analysis, as you can see, very low pressurization rates are recorded, and also the wall temperature increases by only a few degrees. This is reflected in the calculation of the two indicators that I have presented above. Both of them are below the threshold of 0.9 that we set as acceptable criteria to define a safe scenario. And so, in this specific example, the scenario considered can be deemed safe, and the tank integrity is not threatened by this kind of scenario. In the second example, we consider a much stronger fire condition. We have a 6-meter wide fire front with a duration of 8 minutes. Again, we consider a 1 cubic meter LPG tank that is placed 3 meters far away from the fuel bed, generating the fire. Again, two cases were analyzed, a 20% filling degree case and an 80% filling degree case. In this example, the strategy for to carry out the fire source characterization step was actually different. In fact, we used a solid flame model. In this model, the flame is reproduced and is assumed as a solid body with a given emissive power. In this case, we used a value of 80 kilowatts per square meter as emissive power of the fire front. CFD simulations of the tank response carried out in step 2 show that, for instance, for the 80% filling level case, the actual pressure reaches the point where the pressure relief valve opens. In the other case, the 20% filling level case, a pressure inside the tank of about 13 bars is reached. Looking at the temperatures, wall temperatures, it is possible to see that in both cases we reach several hundred Celsius degrees. These results are reflected into the values of indicators that in fact for both cases show that the scenario considered cannot be deemed safe. So thank you very much for watching this video from the WUIVIEW video series. I wish you a nice day. Bye.